12 o'clock, so we'll go ahead and get started for today. Let's see, your tests are not marked yet. They're about half marked, so I've got all the number ones marked and all the number threes marked, and I've got a TA helping me with the other grading. So far people are kind of doing okay, but got to get the whole thing marked before we have any conclusions. I should have those done for you, I guess by Monday, like a week from today, they should be done. You'll know for sure that they're marked when you see your grade go up in Brightspace. Once the grade is posted, they'll be ready for me to give back to you. I'll either bring them to class, or you can drop by my office, or I'll bring them to the lab, so I'll get them back to you that way with your feedback. Before we get started for today, does anybody have any questions? Or want to share any feedback about the test? Okay, so we'll get going for today. Last day we finished up talking about our properties of a conductor. This last point we're going to circle back around to when we cover potential. And then we spent the rest of the class talking about electric potential energy in a constant electric field, and we did that by making an analogy with gravity. When we have gravity, U is mgh. When we have electric potential, U is QES. So that was where we got to last day. We're going to pick up from there today, except instead of having a constant electric field, we're going to figure out what is the electric potential between 2 point charges. And that's a pretty useful thing to look at, because if you think about atomic physics, those are essentially point charges, you know, electrons flinging around a nucleus, so those are like point charges. So this is a good system to understand. Let's say we have a system and it has two charges, Q and Q0. That's what we're going to start with. It says they interact via the electric force, so that's Coulomb's law. Force is K Q1 Q2 over R squared. We're going to have our situation so that charge Q is fixed in place at R equals 0. So this is our R axis. R is going to be our distance relative to 0. And then our charge Q0 is going to move from point A to point B. It's going to move from here to here. So that's the motion of that charge. Notice we're not limiting ourselves to a specific sign of charge. We're just saying Q and Q0. They can be any mix of positive and negative. We're going to ask, what's the electric potential energy of this system of charges, and how does that energy change as the charge moves? So those are the things we're going to look at. So we know that energy is related to work, so we're going to start with the expression for work done by a force. Our expression for work done by a force is that work is the force applied over the distance it moves, and we move from point A to point B. So there's our definition of work done. I guess you saw that in Physics 1050, so this should be an expression you're used to seeing. If everything was constant and simple, it would reduce to F dot delta R, but F changes over distance, so it's F, it's integral of F over R. This dr here, this is the element of the path, or a small piece of the path, and it is a vector and it does have a direction. So this is a small piece of the path. Let's show that on our picture. A small piece of the path might be from right here to right here. Okay, and it's in the same direction of the path. If our QO moves to the right, then our DR is to the right. It has to be in the same direction. This is a scalar product. The dot is important, and we know that a scalar product is you multiply the two magnitudes times cosine theta. So this is the integral from A to B of the magnitude of the force times the magnitude of dr times the cosine of the angle between the force and our element of the path. Are we good to this step? Any questions? All right, so far we really just wrote down our definition of work. and we wrote down our definition of a scalar product. So we know that work can be positive or negative. That positive or negative is usually introduced through this cosine theta. We know that force can be attractive or repulsive. Let's try and put all of those things together. Let's have a tool for figuring out whether the work is positive or negative. So I'm going to think about the sign of my charges, Q and QO, and the sign of the work done as my charge moves from here to here. So I'm going to think about all those two things together. So if the signs of my charges are, they are both positive, or they're both negative. Okay, so if Q and Q0 have the same sign, two positives and two negatives, the force on Q0 is repulsive. Okay, so it will be repelled by Q. If the force is repulsive, I don't really want to draw it on this diagram because I don't want this to get too messy. If the force is repulsive, then it's to the right. That's the same direction as dr. So dr is to the right because it moves to the right. My force would be to the right. So my F would be parallel to my dr. Let's think about what that means. F is parallel. I'm going to spill down onto the next line. So F times dr times cosine theta would be F times dr times cosine 0, which would be F times dr, and work is positive. Okay, so when they're in the same direction, the force is to the right, the displacement is to the right, the work is going to be positive. Everybody good with that statement? Okay. So the next thing we can think about is, what if they're not the same sign? What if they're opposite signs? So if one is positive and one is negative, then the force is attractive. So the force on QO would be towards Q. It would point to the left. My path is to the right. So my F is anti-parallel to my dr. If you don't like anti-parallel, you could say opposite. Doesn't matter. So they're in opposite directions. So then, F dot dr is F times dr times cosine theta. If they're opposite, that's going to be F times dr times cosine 180 degrees. That's negative. In fact, it's equal to -1. And our work will be negative. Okay, so if they're in opposite directions, work is negative. Same direction, work is positive. Okay, let's layer in the last little bit that we have. When we write down Coulomb's law, to date, we've always written Coulomb's law is that our electric force is K times the magnitude of Q times the magnitude of QO divided by the distance squared. And the distance means the distance between the two charges. That's how we've always written it before, is with the magnitudes. Let's ask now, what if we don't write it with the magnitudes? What if we include the signs of the charges? Okay, so let's think about that as we go to the next line in our work. So then our work is A to B. For our F, we'll fill in K times Q times Q0 divided by R squared times dr. If I include the signs here, if my signs are the same, so Q and Q0 are exactly the same, then cosine theta turns out to be 1, and my work is going to be this expression exactly, and it's going to be positive. Okay, so if I include the sign, then I get cosine theta equals to +1, and this is the expression for my work done. If my charges are opposite, then K times Q times QO over R squared times dr, cosine theta would be -1, and I get a negative work done. My negative now can come from Q times Q0. So this expression for our work is valid. It's the same as this one if we include the signs of our charges. So this is the expression for our work done, and here we include sign of charge because it takes care of the sign of the work done. So there's the expression for our work done. This integral is not too tricky. This is certainly one we can solve. So we take our constants out front, k times q times q0. We've got the integral from a to b, 1 over r squared times dr. So for those of you doing math 1001 right now, are you up to this sort of thing? Power law integrals? Yeah. Okay, so this is something you've seen in your math class. The integral of 1 over r squared is -1 over r. And that has to be evaluated at b and a. When it's evaluated at b and a, we plug in b and a for our r values. So that's k times q times q0 minus 1 over the distance at point B minus I'm feeling like I'm going to get bogged down in my negative signs. I'm just going to take my negative to the outside here. Negative q times q0, 1 over rb minus 1 over ra. There, that's a little bit neater. So I just take my negative sign out front first. And then I've got 1 over rb minus 1 over ra. Are we good to here? This line in the integral? So this gives us our expression for our work done. As our charge QO moves from point A to point B, if we know the work done, now we can find the change in potential energy, because we know that change in potential energy is the negative of the work done, because that's the definition of a potential energy function. So there's our work done. So work is minus K Q Q0, 1 over RB minus 1 over RA. I just wrote that down there again so it looks nice and neat. Change in electric potential energy is negative of the work done by the electric force, so negative of this expression, plus K times Q times Q0, 1 over RB minus 1 over RA. Are we still good to hear? So my work is the negative of the potential energy function. So next, this is delta U. Delta U is the change in electric potential energy, the final minus the initial. The final position is at B. The initial position is at A. So let's see what that means for our delta U. The delta U equals our final potential, that's the potential at B, subtract the potential at A. So I'll fill that in here on this side. UB minus UA equals K times Q times Q0 over RB, subtract K times Q times Q0 over RA. Okay. And in this line, I subbed in my delta U on the left side, and I multiplied my K, Q, Q0 in on top of both those R's. Okay, so UB is KQQ0 over RB. UA is KQQ0 over RA. So our general result is that our electric potential energy is K times charge 1 times charge 2 divided by the distance between them. So there's our expression for electric potential energy between 2 point charges. Important in this expression is you include the signs of the charges. And then typical in physics, R is the distance between charges. So if you have 2-point charges, this is how you find the electric potential energy between them. Because our electric potential energy can be positive or negative, it's not a bad idea to think about what does that mean if it's positive or negative. So if the electric potential energy is positive, so Q and Q0 have the same sign, what happens here is that charges will tend to separate. As they separate, R gets bigger and the potential energy gets smaller. If your electric potential energy is negative, the force is attractive, the charges will tend to come together. Then that's sort of interesting. As the charges come together, R gets smaller, U gets bigger, but it's negative. It becomes a big negative number. That's still a lower potential energy, right? Because minus a million is smaller than minus 100. Okay, so it's still towards a lower potential energy. So same behavior. Charges, when released from rest, will still move towards lower electric potential energy. That's just kind of a behavior of the universe. Okay, questions? No? Okay. So at this point, so far we've got 3 equations that all kind of look the same. Force is K, Q1, Q2 over R squared. Field is K, Q over R squared. Electric potential energy is K, Q1, Q2 over R. Make sure you're able to keep all those equations straight. We're going to get a 4th equation, and then I'll put them on a sheet and I'll label them for you to keep them together while you're studying. Okay, good. So let's do some examples. So let's start with something kind of straightforward. Let's go right to an atomic example. Find the total mechanical energy of a hydrogen atom. In a hydrogen atom, the electron in the atom will orbit the proton. The proton is in the nucleus with a speed of 2,188 kilometers per second, and the distance is 52.9 picometers. So let's find the total energy here. Mechanical energy, E, is kinetic energy plus potential energy. Let's make sure we understand what we mean by each of those terms. That's the kinetic energy of the electron plus the kinetic energy of the proton plus the electric potential energy between the electron and the proton. Okay, so 3 terms in this equation to calculate. Our electron will have a kinetic energy of 1/2 times the mass of the electron times the speed of the electron squared. Proton is 1/2 times the mass of the proton times the V of the proton squared. The electric potential energy is Coulomb's constant K times the charge of the electron times the charge of the proton divided by the distance between them. Okay, so we filled in our equations for kinetic and potential energies. Let's simplify a little bit right off the bat. In a typical atom, how fast is the nucleus moving? Not very. Okay, so a nucleus typically doesn't move around a whole lot. We're going to say that the speed of that proton is an awful lot smaller than the speed of that electron, so that one's going to be negligible. That's not going to count very much. So let's see what else we have. 1/2 the mass of an electron, 9.11 times 10 to the minus 31 kilograms. Our speed is in kilometers per second. We should work in SI units. So that's 2188 times 10 to the 3 meters per second. Don't forget to square it. Plus K, that's 8.99 times 10 to the 9 newtons meters squared over coulombs squared. The charge on an electron is minus 1.6 times 10 to the minus 19 coulombs. Charge on a proton is plus 1.6 times 10 to the minus 19 coulombs. Divided by the distance between them, that's given us 52.9 picometers. A picometer is not one of those units I expect you to remember. Once in a while I'll use it in class because we can just look it up, or we could just remember it. That's times 10 to the minus 12. Okay. So that's not a prefix I'd expect you to know on a test. When we put those in the calculator, you get 2.18 times 10 to the minus 18 joules, minus 4.35 times 10 to the minus 18 joules, gives us a total mechanical energy of minus 2.17 times 10 to the minus 18 joules. Questions to here? Yeah?
Should we always expect like low mechanical or low energy in general with these subatomic?
Oh yeah, that's a good question. If not everybody heard it, is do you anticipate these energies being small? And I would say absolutely. The masses are teeny tiny, the charges are small, so typically those will be small energies. Yeah, good question. One thing you might ask, because this can sort of be tricky conceptually to understand, is what does it mean that the total energy is negative? Fundamentally what that means is that that atom likes to stay together. You'd have to do work to it in order to bust it apart. So a negative energy would be a stable situation, so that's something that likes being together. Okay, question? Okay, let's do an example with a little bit more meat on it. So I've got to zoom out on this one, I'll try and write bigger. A proton is fired from far away at a 1 millimeter diameter glass sphere. The glass sphere has a charge of 100 nanocoulombs. A nanocoulomb is something I would expect you to remember. What initial speed do we have to give the proton so it just reaches the surface of the glass? So my picture here is intended to represent the initial and final situation. In my initial situation, my proton is fired from far away. That means it's moving. Right? It's got some initial velocity, VI. It says far away, so our initial separation is from here to here. Initial separation we would call RI, so this is initial. It doesn't say how far away, it just says far away. So we're going to say our initial is a big number. So that's from here to here. So that's our initial setup. Our final setup, down here in this box, the proton has just reached the surface of the sphere. Okay, so it just reached. That just reached does a lot of work. If it just barely makes it, that means that the speed it has when it gets to the surface is 0. Okay? If it wasn't 0, then it could have kept going. It wouldn't have just barely made it. So that tells us that VF is equal to 0 for our proton. And it also means that it's just at the surface. So the distance is always between the centers of the charges. RF. This is the radius of our glass sphere. So RF is the distance between the center of our proton and the center of our glass sphere. Our glass sphere has a radius of 0.5 millimeters. How big is a proton?
Negligible.
Small, okay? Negligible, small. So our final distance, RF, is about 0.5 millimeters. Everybody okay with our picture for initial and final, our setup? Okay, what initial speed do we have to just reach the surface? So when we did problems when we were shooting protons between the plates of capacitors, I said that we could, if we wanted to, use kinematics. That would be a totally legitimate way to do those problems. Do you think we could use kinematics here? Okay, I got a couple of head shakes. Anybody want to say why you can't? Okay, so the instinct to say no, you can't use kinematics is absolutely correct. When we do kinematics, you know, V is V naught plus AT, X is V naught T plus a half AT squared and all that business. That's all for constant acceleration. For this one, the force between two charged particles, it depends on how far apart they are. So as the distance changes, the force changes. As the force changes, the acceleration changes. If you have a changing acceleration, you can't use kinematics. That's why you can't use kinematics for this problem. It's because the distance changes and the force changes. Okay, so then that means this has to be an energy problem. We're going to use conservation of energy in whichever form we choose to write it. I will say that our final energy is our initial energy, plus work done by any non-conservative forces. We're going to say that there's no friction, there's no appreciable air resistance. So there is no work done by non-conservative forces. Our final energy is our final kinetic plus our final electric potential. That equals our initial kinetic plus our initial electric potential. Okay, good to hear. Let's figure out each of those four terms. Let's put them together. Let's see if we can find our final speed or our initial speed. So our initial kinetic energy, K initial, is K initial for the proton plus K initial for the glass. The glass sphere is not moving around, so that's 0, equals 1/2 times the mass of a proton times VI squared. Okay, so there's the initial kinetic energy of the whole system. Our initial electric potential energy is Coulomb's constant K times the charge of the proton times the charge of the glass sphere divided by our initial. If our initial is big, because it's far away, then UE initial is small. Small compared to everything else we're doing, so it's about equal to 0. So when you have something that's far away or something that's big, we're kind of approximately infinity, right? So RI is close to infinity. That makes this thing close to 0. So when things are far away, the potential energy is about 0. So that deals with our initial. Let's deal with our final. So K final is K final of the proton plus K final of the glass sphere. Glass sphere is still not moving, so we've got 1/2 times M times VF squared. VF is 0 because we said it would just reach, so the final kinetic energy is 0. Okay, so at the end, nothing is moving, no kinetic energy. Our final potential energy, UEF, is K times the charge of the proton times the charge of the glass sphere divided by RF. So there's each of the four terms that goes into our energy equation. So let's plug them all in and see what we get. So our conservation of energy was KF plus UEF equals KI plus UEI. First thing we'll do is we'll cross out our zeros. KF was 0, UEI is 0. So our final potential energy has got to be equal to our initial kinetic energy. So all of our kinetic energy transferred to potential energy, it all transformed. Our final electric potential energy is K times the two charges divided by the distance equals our initial kinetic energy, 1/2 times the mass of the proton times VI squared. In this equation, we know everything except VI, so we can find that initial speed. We can see how fast we had to shoot that. So VI is going to be 2 times K times the charge of the proton times the charge of the glass divided by RF divided by the mass of the proton and take the square root. Okay, so I just did those steps in my head. I'm guessing everybody's okay with that, even if you would write them down for yourself. This would get real tangly if I filled in all the numbers in one line, so I'll just put them here on the side. Charge of the proton is plus E, 1.6 times 10 to the minus 19 coulombs. Charge of the glass sphere was given 100 nanocoulombs, or 100 times 10 to the minus 9 coulombs. The final distance was our 1/2 of a millimeter. Mass of a proton is 1.67 times 10 to the minus 27 kilograms. That's all of our numbers. Put those in the equation and we get 1.86 times 10 to the 7 meters per second. That's pretty fast, but it's not faster than light, so we're kind of okay with this. So we're shooting this charge. We want it to get really close to a pretty big charge. It makes sense that we had to shoot it pretty fast. Okay, any questions? Yeah?
Can you please repeat why we can't use the kinetic?
Sorry, what about the kinetic?
Can you please repeat why we can't use the
Oh, why we can't use kinematics? Okay, so if not everybody caught it, the reason we can't use kinematics is because that applies to constant acceleration. Our force here is the electric force, K Q1 Q2 over R squared. As the distance between the charges gets smaller, as it moves closer, R changes, so the force changes. If the force changes, the acceleration changes, and if A changes, you can't use kinematics. Okay, so the next slide in the notes is basically this question except opposite. We have two charges and we want to shoot them apart instead of shooting them together. So I'm going to post the solutions for that for you to work through. But it goes through it uses the same ideas that we did in this example. Okay, questions before we move on? No, we're good. So our next example, we're going to build step by step. There's going to be a bunch of things happening. Right at the beginning of the problem, we have one charge and a second charge. They're held at rest, so these things are held in place. They're not free to move. And we know the initial separation. So this is our starting point. Part A, find the electric potential energy for this configuration of charge. So this one is familiar for what we've done so far. So for part A, and we'll do diagrams as we go, we have one charge here. I'm going to call this one Q1, 1.11 microcoulombs. We have charge Q2 over here. Q2 is negative 2.22 microcoulombs. They're separated by a distance R equals 10 millimeters. And our question is to find the electric potential energy between them. So this is just going to be our equation for finding electric potential energy. So the electric potential energy, I know there's a third charge coming, so I'm going to start to be careful with my subscripts. This is the electric potential energy between charges 1 and 2. I just want to be careful so I don't get confused later. is K times charge 1 times charge 2 divided by the distance between them. Fill in our K. Fill in Q1. You remember that microcoulombs means times 10 to the minus 6. Fill in our Q2. Don't forget that we have to include the sign of the charge because the potential energy can be positive or negative. Divide it by our distance. Got to put that in meters. And what we get for our answer is negative 2.22 joules. Any questions here? So there's the electric potential energy of those two charges together. Part B is different. We bring in a third charge, also negative, and we hold it at rest there. Now find the electric potential energy. Okay, so we're going to move to a system with 3 charges. So I'm going to draw a new picture and we'll find the potential energy again. So part B, charge 1 and charge 2 are exactly where they were originally. I've brought in charge 3, and I'm placing it at 10 millimeters from the original 2 charges. So 10 millimeters from each of them means it's down here, and we're on an equilateral triangle. Okay, so there's our picture. We know our Q1 is 1.11 microcoulombs. Q2 was negative 2.22 microcoulombs. Our new charge, charge 3, is negative 3.33 microcoulombs. And our question is, find the electric potential energy of this system of charges. So we have to figure out how that works. Potential energy is an energy of interaction. We get potential energy whenever we have 2 charges close by. So that means Q1 and Q2, they interact by the electric force. They have a potential energy between them. Q1 and Q3, they interact by the electric force. There's a potential energy between those 2. And Q2 and Q3 interact by the electric force. There's a potential energy between those 2. So if you're finding the potential energy, you have to add up all of the combinations. Okay, so this is what we do when we have a system of a system of charges. So our total UE is the potential energy between 1 and 2, plus the potential energy between 2 and 3, plus the potential energy between 1 and 3. Okay, so there's our idea. This is definitely something we can do. We've got part of it already done. So the potential energy between 1 and 2 we already found. So U12 was negative 2.22 joules. U23 is K times charge 2 times charge 3 divided by the distance between 2 and 3. Fill in our numbers. And the potential energy between charges 2 and 3 is plus 6.65 joules. Okay, so that's between 2 and 3. Last I need to find 1 and 3. So I just fill in all that information. And the potential energy between 1 and 3 is minus 3.32 joules. Okay, so there's each of the three combinations. To find our total electric potential energy, we just add those numbers up. So UE equals U12 plus U23 plus U13, 1.11 joules. Okay, any questions to here? So the important bit to take away here is that you have to get all of the combinations. Okay, part C, we let go of our Q3 and we let it move. How does it move and what is the work done by the field? Think about the sign of the work done. Okay, so let's think about what happens to it first. So here's our picture. And in fact, why don't I just sketch down our picture again, because I want to put all those plus and minus signs on there. So part C, charge 1 here, that one's plus, charge 2 here, charge 3 here. So what's the direction of the force between 1 and 3, attractive or repulsive? Attractive, because they're opposite. What's the direction of the force between 2 and 3? Repulsive. Is this force bigger or smaller than this force? Bigger. This is a bigger charge, so it's going to have a bigger force. So ultimately, Q3 will move away. So if you think about it from a force perspective, that certainly works. You could also think about it from an energy perspective. The potential energy of this configuration of charge is positive. It will always move when released to go to a lower potential energy to be farther away. So you could think about it from an energy perspective as well. Doesn't really matter. Okay, so that's how it moves and why. Find the work done. So work done is negative the change in electric potential energy. So that's going to be negative our final potential energy. Subtract our initial potential energy. So let's think about what those things are. So our initial electric potential energy is when all of those things are in place. UEI is 1.11 joules. Our final electric potential energy is when Q3 is far away. It's going to move away until the potential energy is small. So our final electric potential energy would be the energy between 1 and 2, plus between 1 and 3, plus between 2 and 3. But Q3 is far away. These things are about 0. Okay? When charges get far apart, the potential energy gets very small. So our final electric potential energy is about equal to the potential energy between 1 and 2 only. And we found previously that that was minus 2.22 joules. Right, so then our work done is minus our final potential energy, negative 0.22 joules. Subtract our initial potential energy, 1.11 joules. Our work done turns out to be positive 3.33 joules. So that builds on work is negative of the potential energy. Why is the work positive? If you think about the direction of force and the direction of displacement, when we let this go, it's going to be pushed away by the electric force, by the net electric force. It will move in the direction of the force. Those two things are parallel. That gives a positive work done. So that's why the work is positive. And then part D is find the final speed if the charge has a mass of 3 milligrams. Okay, so find the final speed if the charge has mass 3 kilograms. I think we've got just enough time to get that bit finished. Any questions here before we move on? Yeah?
Won't the number 1 electron have effect on the third one?
Not when it's far away. right? When it's far away, that distance is really big, so the potential energy is really small. Yeah.
Why is particle 3 moving up particle 2?
Because these two are held in place, we've only let go of number 3. So those are still pinned to the table or whatever. Yeah, great questions. Okay, part D. Find the speed of our last one. So, a couple of ways you can jump into it. I'll go right from the work and energy, just right from energy. So part D, final electric or final mechanical energy is initial plus work done by non-conservative forces. No friction, no air resistance, nothing like that. No work done by non-conservative forces. Our final energy is Kf plus UEF. Our initial energy is Ki plus UEI. Ki, let's see. Ki was equal to 0 because we release it from rest. Kf equals UEI minus UEF. UEI, that was our 1.11 joules. UEF was our negative 2.22. So that equals plus 3.33 joules. So there's our final kinetic energy. You also could have got here by work is change in kinetic energy. That would have been okay too. Same statement, just different ways to get there. Kf is 1/2 times the mass of charge 3 times the speed of charge 3 squared. So V is going to be 2 times our energy divided by the mass. Got to take the square root. The mass, sometimes this feels a little bit tricky. The mass is 3 milligrams. A milli means times 10 to the minus 3. So that's 3 times 10 to the minus 3 grams, because that's what a milligram is. And a gram is 10 to the minus 3 kilograms. So a milligram is times 10 to the minus 6 kilograms. Put that through the calculator and we get a speed of 1,490 meters per second. So when it gets very far away, it's going pretty fast. Okay, that's 2 minutes left, but we'll quit there because we don't have time to do the next example. And this is my day to run to my next class. So if anybody has any questions, just come see me this afternoon.